Thank you very much for having me this afternoon. So I've been on a bit of a whirlwind tour of Singapore the week before last, Davos last week, and now Brentford. So pretty much all the best places in the world that I can imagine anyway. So a bit of a talk this afternoon around the work that we've been doing at the Alan Turing Institute, where I am the Mission Director for Sustainability, and also I have a position as Professor of Data-Centric Engineering at the University of Southampton. So employed by the university 1 day a week and seconded to the Turing for 4 days. So it's a really real pleasure. Alan Turing Institute being the UK's national AI and data science institute, housed at the British Library in London. So lots of opportunities for us recently. I've been working in AI for about 20 years now, so well before it was cool. And so it's been nice over the last 5 to 10 years for people to actually notice that we're doing some interesting things and seeing it turn into applications. I'm going to talk a little bit about sort of my back history of where we've been applying these tools and sort of doing the initial work to demonstrate the usefulness, but then a little bit about the future and where I see this going and the big problems that we have around doing this at scale. So the sheer quantity of data models that we want to build, how are we going to do that? And hopefully starting on some approaches to that. So I think we're living in an increasingly unsafe world. And within the sustainability mission, we don't believe that we can wait for net zero solutions. So the world was literally on fire last year due to climate change, increasing the effects of fires in Los Angeles. We're seeing droughts in India. And last year, we were at an average temperature of above 1.6 degrees, which is higher than the agreed 1.5 that we thought we were going to meet. And I think it's increasingly unlikely that we meet those targets. Year on year, we are likely to be going higher than plus 1.5. And if we go to 1.5, there's a 1 in 10 chance we get to 2 degrees, which is really when we start to see catastrophic effects, and when we'll start to see people spending more money on stopping the effects of climate change than actually being able to stop it. So there's a spiraling effect. We do believe that AI can have an immediate impact on this. So we think that AI can stop or can reduce emissions immediately. We can apply this. And why do I say that? We've been part of a number of projects where we've applied AI in the real world and been able to reduce emissions. So in shipping, we've seen potential reductions of 18%, real world emissions certainly in around the 5 to 7%. We looked at a pharmaceutical building and optimized the HVAC system, reducing emissions by 42%, which is quite large. And we actually created an underground urban farm. So that's a picture from London where we created this digital twin of an underground farm. Great thing about the underground is that you control all of the climate. So you can change the temperature, you can change the lights, you can change the humidity, and that allows you to actually optimize the plant growth. And by basically taking a model of the plants, taking some data from the plants and updating the model and changing the atmosphere underneath, we were able to increase the yield by 24% using 100% sustainable energy for that. So some really nice ways in which we can actually utilize AI in the real world to reduce emissions. There's obviously got to be a little bit of a catch, otherwise problem solved and I wouldn't be here. But I'm going to talk a little bit about what we mean by data-centric engineering, because I think this community probably talks a little bit differently from perhaps my background, which is sort of like more along the mechanical engineering, aerospace engineering route. Now, I'm Professor of Data-Centric Engineering. My boss says that that's a terrible name for a job title, because all of engineering has been data-centric for as long as we can remember. So dating back to the Egyptians, 5000 BC, they actually built the pyramids by trial and error to some extent, building pyramids, and when they worked, they continued that replication. And when it failed, they tried not to replicate those processes and moved on. And there's written down evidence of this in their design and construction. Lord Kelvin said, if you cannot measure it, you cannot improve it. A very clear thing around how we need data to basically make and optimize our processes, all the way through to places like Toyota, who've had a really rigorous process of gathering data and utilizing that to improve how they design and manufacture cars. But we think there's been some changes over the last probably 5 to 10 years. One of those is around compute infrastructure. So we have access to compute that is just phenomenal. Right now, one of my PhD students is building a large language model that can solve the sort of mathematical problems that you can see on the screen. The sheer quantity of compute that requires is unimaginable 10 years ago, and that is increasing year on year. And in 5 years' time, 10 years' time, when we see quantum, it's going to explode even further. We see measurement and instrumentation via whole sensor networks, so we understand our systems so much better than we've ever understood before. So the picture up there is a 3D printed bridge that we built, and that has sensors placed all the way through the bridge so that we can measure vibrations, so that we can measure noise, we can measure pollution. And so you have like this living city effect if you have all these bridges through the different areas, and by 3D printing it, you can use unusual shapes that wouldn't actually meet regular construction design rules. And through that 3D printing process, we get very large thermal changes through the bridge materials. And the only way to ensure safety really is to have that constant monitoring to understand how it's been built and how it's operated. And so we're going to see this more and more in different places, more and more sensors that tell us how stuff works. And what it was actually built like. We have data at multiple scales in time and space, so we have much better understanding of what our climate is doing, what the weather's going to be like, and we can utilize that within our models. And that's leading to new theories, new technologies, new markets and business models, as well as new education and skills. So we're seeing the way in which AI is completely transforming that thought process. And often it's not really the data tools that are the problem, it's the business models. So if you're looking at around automation right now, a lot of them aren't really struggling around the autonomous car technologies. They're trying to work out how to actually make money out of having an autonomous car and where the liability stands. So we're seeing quite a change in how you implement this. That picture is a composite material that we designed with an AI, and it has a 1,050% improvement of strength to stiffness ratio compared to the standard materials that you would see. So it's like a substantial improvement in what you would want to use that for. That could be used in lightweighting for drones to improve the wings, could be used in sort of foldable satellites, that sort of thing. So there's this way in which AI is allowing us to generate these whole new exciting areas, and we need to think around, how do we actually utilize that in the best way. So coming back to my shipping problem, we have more sensors, we have better data on the ships than we had 5 or 10 years ago. And so now we can understand the operation better. We can change the draft and the trim, we can change how the ship sits in the water, and that allows us to reduce fuel usage. We can navigate more clearly, and that allows us to further reduce the emissions. In fact, it also allows us to avoid hitting whales, which is really nice, so we can increase some biodiversity issues as well. So we can map where the whales are in the world and actually route around that and do that dynamically. So there's some really nice advantages to this, but what's the kind of key problem? Well, this is a graph. Finally get to some graphs. As an academic, I should have some stuff. I don't think I put any equations in though, so I feel like I'm letting you all down, but maybe if I come back, I'll do a hardcore maths AI talk. But there's some some graphs here of effectively the standard ship performance at 10%. So if we use models that were developed from towing tank tests, they're about 10% errors from standard shipping. And they're relatively good. It's what we've been using for a long period of time. Well, now we can actually utilize data to do the same thing. And what we did was we took 9 ships, we took the data from 8 of those ships, and we predicted the performance of the 9th ship. And we had a look at what the errors were from that. And we looked at when we got non-sister ships, you can see the performance is worse than a standard ship model. So that's not really ideal. So if we want to share data between non-sister ships, it's probably not really going to be something practical. So we have to have at least the same type of ship, data from the same type of ship. When we shared that data across, we ended up at about 10% errors as well. And so the only time when we actually get this improvement compared to a standard model is when we use the data from the ship itself. So that means that every single ship that we have, we're going to need to have a bespoke model. Now, some companies will operate up to 2,000 ships on any given day. It's quite a lot of ships. If we take Shell, for example, they operate around that number. They own 30 ships, and so that means that you've got almost 2,000 ships that are on charter. So they're renting them out in different agreements. Now, they can have weekly charters, daily charters, monthly charters. The ships that they have are constantly changing and adapting and moving. So that means to be able to understand the operation and gather the data, they have to constantly be changing what they're doing, different sensors on board the ship, different ways of doing it. It becomes actually very, very difficult to actually provide these types of solutions. And when you think about a 5% reduction in fuel, then some of these ships burn, probably 50 to 380 tons of fuel a day. It's a lot of tons. So let's call it 100, because my maths is not great, getting old. And so if we call it 100 tons, it's 5 tons of fuel a day from a 5% fuel saving. In terms of CO2, that's 15 tons. It's quite a lot. So if we can start to scale these tools, we can start to get to the point where we're saving huge amounts across that fleet of 2,000 ships, but we need these bespoke models. So I think the development of these data models is becoming increasingly simple. I can get undergraduates to build the models themselves, but the problem is the data's ugly, it's constantly changing, it takes a long time to clean. The shipping data for us takes about 2.5 days of cleaning before we can utilize it. And so you want to do 2,000 ships, that's a lot of cleaning. The other problem that we have is that most of the companies don't have the digital backbone to be able to utilize that data. So they don't store it in nice ways. I've spoken to quite a few people already about companies sending me Excel sheets. Each month is in a different Excel sheet. It's not a nice way to do it. So you can't really utilize that unless you do it. So if we wanted to go to a company that was, say, looking at 10,000 ship models, how do we do it? I know that the company I work with, Silverstream, who are in London, they build data models for about 70 ships at the moment, and they have about 18 data engineers. So to get to 10,000, you are talking lots and lots of people, skilled people, expensive people. I spoke to a car company, and they want to have a digital twin of every component on each car by the time they go autonomous. They have 60 million cars on the road right now, so let's call it 10 components. That's 600 million digital twins they want to build. That's a lot of digital twins. Let's say it's 100 components, it's 6 billion. So you could hire every data engineer in the whole world, and you cannot possibly do what they're trying to achieve. And so it's very clear to me that we have to start looking at how we automate these processes so that we can take time away from the people doing this so they can focus on the quality assurance aspects and try and scale. So we need to automate the training, the quality assurance, and the communication so that we can, and what we wanted to see is whether we could start to develop an AI data engineer to create a bespoke data pipeline. And so it's a bit of a moonshot project we're working on, but how do we start building towards that vision, that future? So our AI data engineer has to take this raw data, has to do some data processing, some cleanup, needs to structure the data and put it into a database. We need to be able to create the AI models and train and fine-tune those models and quality assure them. And we need to create insights and interact with the end user for these to become useful. So if I go back to the routing of ships that we talked about, we have a commercial product that does that. A lot of the ship's captains don't actually follow the routes because they think they know better than the software, although we have done lots of maths to demonstrate that is not the case. Why? Because they don't have trust in the system. And so currently we're working on a tool that actually allows the ship's captain to communicate to that software and respond in a manner that actually works for the ship's captain. It can't be very, very long because they don't have time to communicate with it. It needs to have all the correct information in the right places. So we're trying to work through that, interviewing ship's captains to understand that process. So that's the sort of thing we're talking about. I'm not going to talk all the way through this because I've heard starting at the beginning is a very good place to start. And so we're going to just talk through the sort of structuring data approach that we've got to so far. This is not complete. And so we are very far away from perhaps being able to replace an AI data, or to create data engineer, or to replace data engineers as we stand. But hopefully it sort of shows a sort of direction of travel and some of the problems that we've had along the way. So when we started, we thought, okay, this is easy, right? We just create a user prompt, we stick it into Cursor, and then basically we get something that we can stick on the cloud, and then we have a database. The problem is that we realize that we're a bunch of AI engineers and we have no idea how to build a database or what a database looks like. And so our first port of call, probably similar to most of the people who would be using this tool, is that we probably need a step between us and Cursor to allow us to actually determine and justify what that database looks like. We actually need to get some advice on how to build it. So we started with a very simple approach. We thought, we'll ask a large language model. That will make everything very easy. We send a prompt, and hopefully we get a JSON file with some pipeline specifications and see what happens. It was not good. The results that we were getting were extremely poor, and when we tried to actually run this and compile it, we got nothing useful. It was so far away that we actually thought there was a really big problem. This was about a year ago, so it's quite interesting. I actually got my team to go back through last week and retrial this on ChatGPT-5, the early experiments. And you can actually see now that even within 1 year, the ability for like a large language model to actually specify some elements of it is starting to get there. So what I've done is some snippets of code all the way through some of the snippets from the JSON file. There's like more detailed versions in a paper that we've written, if you're interested, which gives the full output, and you can look through that. But this just looks at component 1 each time, which is the same component, so you can get an idea for what it's giving out. And you can see here it gives some information. It's got a name. It tells you the purpose a little bit. It doesn't tell you what's good or bad about the system. And it gives some idea of what AWS you should actually be using. I'd hoped that we could actually try and compile some of these to show you what the outputs were, but we didn't have time last week. But we're just running through a process of seeing how close to compilable these actually are from the different versions. But I think what's interesting for me is that how much we've moved in 1 year from state-of-the-art large language models last year to this year, and a sort of massive step forwards in what they can already achieve in a 1 year period. So if I give this talk in another year's time, what sort of outputs will we be getting from there? But we felt that there's a couple of problems, not only with the outputs of this, but also around the whole process. So if I'm building a data pipeline, if I've got a workflow, what I don't want is a key component of that changing every year and that I have no control over. So if I put ChatGPT-5 at the center of what I'm doing, then when ChatGPT-6 comes, do I have to rewrite the whole thing to wrapper around that? Do I have to change the prompts? Do I have to re-prompt engineer? This can be very difficult and time consuming. Also, I don't know if anyone uses this stuff, but it costs a fortune. Like doing it over and over again, really, really can start to build up some costs. And then for me, as a sustainability person, ChatGPT-5 is not like the best in terms of energy usage. And so we have a few things that we might want to do to try and reduce those models down. And a lot of the emphasis at the Turing right now is around small language models. So we've got a big focus on how do we take those very large models and distill them down into something smaller that we have more control over, that we can train as an individual company, and that we actually can see how it fits into the workflow. So we started to explore some multi-agentic approaches to this, mainly because it's very popular right now and very cool. So we thought, why not get us some good journal papers? Always nice for an academic. And what we did was we basically justified a pipeline design team of agents, each of which has their own job role. So they each have a separate prompt, and they have a different role within the element. They talk to each other, and basically through that process, they start to design the pipeline, much like a team of people would do. And I like this approach a lot. A couple of, issues with this at the moment for me is one, these are all the same large language model. So while it's a multi-agent approach, it is only one agent with different prompts. So that's something we're looking to solve in the future with a really truly multi-agentic approach. And the other is there's quite a lot of work around deciding the right number of agents to have in your teams. There's still quite a lot of design effort that goes into this. We're trying to take that away from the end user, and we're looking at some sort of way of generalizing this as well over the next year. So some improvements to make, but I think it shows some promising bits. Ooh, apparently Copilot really wants to talk to me. What we found was the problem is that LLMs actually have this huge memory limitation, which is quite funny considering the fact that how much stuff they can actually fully memorize. The focus, I don't know anyone who reads a lot about large language models, but a lot of the focus has been around these very long context windows that we've seen and discussions of that. That's why transformers are really good. But what we found is the problem is not that the stuff falls out of the context, but the distance from the current area we are to that prompt. So effectively, they're part of the conversation. It's there, but it's starting to move so far away, the agent can't make use of it. So it's got it in its memory, but it's struggling to find it. It's not making use of it. And so what we found was that as these agents went round and round in the conversation, they were like super unhelpful. Every single time it came back around to the agent, rather than building on what had been said before, they were actually saying something totally different. So, like, instead of saying like, oh, like we could make some small adaptations to the thing I said last time, it's just like, let's do something completely out there. And what we were finding is rather than spiraling towards like a conclusion, we were spiraling away from a conclusion, that these agents were really struggling to actually utilize that contextualization. They also forgot the user's instructions. So partway through solving the problem, they effectively forget what we'd asked them to do, and they started to solve different problems entirely, which is kind of neat, but not that helpful to us. So what we decided to do is implement this approach that we've called intrinsic memory. And this is basically to retain structured contextual memory right by the agent. So each time the agent says something, it then saves that to the prompt. And so that effectively, when it comes around next time, its memory is augmented by this conversation of where it was last time, so the last thing it said. The interesting thing about this is, one, that it's got that prompt right there of what it's just said. But two, we start to see heterogeneity between the agents now, because each agent has a different memory. And so each of us in this room, when we leave here and we go home, we'll take away a different memory of what this conference was about, what people said. Each of you will take away something different from this talk. And now we're allowing our agents to do that in the same way. There is some build-up of this contextualization and heterogeneity, which is allowing them to perform better as well. And this is something we plan to expand on as we go forwards. So effectively, all we do is we take the current memory and we append the current output as a couple of prompts. So it's quite a simple system. And actually, we can build the templates, and we found that the templates don't need to change between tasks. So we can just use exactly the same templating each time, which is allowing us to actually solve quite a range of different problems now without making too many design changes. And if we have a look at the difference, some more graphs, nice, like between them, basically the blue is our intrinsic memory approach, and the red is the baseline multi-agentic approach. And we basically try to judge them across scalability, reliability, usability, cost effectiveness, and documentation. See, we perform better than the baseline on each of them, which is nice. And you can sort of, the way that we've actually generated these is that we got the outputs and we got another large language model to tell us how good they were on each of these different things. So it's quite interesting now as an academic approach. A rigorous scientific approach allows us to use a large language model to rate the readability of a different item. But this is now becoming quite stock as a smaller side. But effectively, our large language model thinks that our approach is better than the other large language model approach, which if that's not confusing, I don't know what is. In terms of showing us actually what happens, sitting up next to the ChatGPT 5 results, so just flat out what would happen. I think the multi-agentic approach, I'm not sure that really helps you build a database at all. It's got a name for the component, which is nice. The description basically just reuses the name. And it's got a couple of ratings of how difficult this is to implement or maintain. But I'm not quite sure how that came about or how useful it is. So from a human user perspective, we're not really gaining very much from this approach. I don't think it's really helping us understand what's happened. And I think if we put this into Cursor, I don't think Cursor is going to give us anything useful whatsoever. There's no naming of what the component would be or where we should get it from. So quite a few problems with that. But when we go to the intrinsic memory approach, and I'm really sorry, it is quite small, but there's a lot more text here, which I guess is good. We can start to see that there's a lot more kind of details around how it would actually be formatted, like what it would actually use. It's got some pros and cons that are kind of a bit more explicit, and we're starting to see some closer to what we would want to see from a specification coming through. And so I think what's interesting for us anyway is that ChatGPT 5 is a 1 to 1.5 trillion parameter model. So very, very large. The one on the right, we use a 3 billion parameter open source model that you can download off Hugging Face and utilize tomorrow. And that would fit on, the sort of compute you probably have access to within a company. And so you can then control that much more easily. You've got the ability to store it, understand how it's used, and there's no updates going on behind, and it's also totally free. So I think some kind of nice advantages to how we can build that approach around what we're doing. So the next stage will be testing this and actually seeing how well it builds the database, and then also starting to pull data into the database as well. So we've got some companies who've given us some data so we can actually start trialing this. I'm sorry we didn't quite get to proof of concept on this, but hopefully in the next few months we'll start to see something interesting. And if you see me give a talk again, maybe I'll have some nice video of something a bit more useful. But I think what's interesting here is we managed to maintain contextual consistency across the conversation. We've been able to reduce the size of the model that you require and really bring it into something that you can probably use at home. We've reduced the energy usage by a large scale, and we can improve the conversational and output quality as well. Next stages will be to start to give the agents personality so that they can work together better, and start to see the way in which we can generalize this across different problems, not just the data pipeline, but anything else as well, by being able to have like a corral of different agents that would fit into our team and have a selector agent. I've called it a Nick Fury agent, like an Avengers Assemble type thing, where basically you can pull the right data engineers into the team for the given task. So hopefully that was at least mildly interesting. Thank you very much for the time, and I'm happy to answer any questions.
Wow, you're really busy with a lot of things. So I wanted to ask you some examples of the variables that you collect from your ships, for example. I imagine that there must be something about the weight, about the engine, about the age of the, I don't know. Can you give some examples?
Yeah, so the way that we've done it currently is that there are about 99 different variables that are collected from a ship normally in a sort of stock approach, give or take depending on the system. We actually just utilize 7 of them. 7, yeah, which don't even utilize the weight or the length of the ship. So we use the power, we use the speed, we use the wind direction, the wind speed, the wave height, the draft and the trim of the vessel, and from that we're able to derive the power just from those parameters. And if you remove the wave height, you actually only change the error by 0.5%. And since it's a very expensive parameter to get, I normally recommend you don't bother unless you already own that data.
Thank you very much.
Going down to the lines of sustainability, if these ships are generating so much CO2 all over the world, and CO2 is our main gas warming effect, why don't we put the big collectors on there and actually have a CO2 factory that when it arrives at port, it can drop the containers off, and so we don't actually need so many onshore CO2 packaging things or gathering of nitrogen to put into food packaging?
Yep, so that's actually starting to be looked at. There are people building those technologies or exploring those. There's just nothing available on the market. And my belief is that we need to reduce emissions now rather than waiting 10 or 15, 20 years for these technologies. The other things that are being explored are things like ammonia, hydrogen, methanol as alternative fuels, which are net zero. But again, these are unlikely to be in place before 2040. And so I think there's the sort of approach of waiting, or we can do something about it now. The other thing is that whatever the option, it's going to be really expensive. And if you can start saving $600 per ton of fuel per day now, that helps you build up some money to be able to deal with the expenses of some of these additional technologies. Net zero fuels, the lowest estimate I've seen is 3 times more expensive than diesel. And when you're talking about companies having $1 billion a year of fuel bills in some cases, 3 times is painful. Any other questions? Well, interesting. One of the main things that we're shipping around is fuel for ships. but yes, agreed. I feel like we're probably in a place of global trade where that's unlikely to happen. There are predictions that with 3D printing that shipping will go down, but most of the predictions I've seen are a 3 times increase in global trade between now and 2050, which it means that shipping will be doing more of the task than ever. So yes, every time you buy something, think about the CO2 usage, but always difficult to do. Yep, so sales are a big option. They are useful. I've seen estimates of up to 100% fuel reductions from people selling sales. Although, and I do realize we used to sail all over the world, but I feel that for most of what we do now, it's unlikely that they'll give those. More reasonable estimates are probably about a 20% reduction from wind assist type of approaches. But you should start to see these happening more and more. I saw one in Naples maybe 10 years ago with a ship with sails on. And they are increasingly becoming important. The problem is perhaps also working out the difference in routing that you'll see from ships with sails and the directions in which they'll travel. And that could affect megafauna and other important habitats around the globe. So we need to be a little bit careful as we reroute these vessels that we save the fuel on one side, but we also think about what the other impacts of changing how we actually do things can have on the rest of the ecosystem.
Any more questions? No? Thank you very much. That was very interesting.